Hello everyone, welcome to the next class on the probability and statistics. Today we will discuss about the next property of the point estimator called as consistent estimator. So as the graph look like says that this consistent estimator is nothing about discussion about the variance. So let's start with this video. Myself Dr. Garg, working in the School of Mathematics, Thapar Institute, India. You can contact me either of my email IDs or else follow this channel for more updated videos. So we all know that for any of the estimator is said to be the good estimator if it is satisfy the certain properties such that unbiasedness, consistency, efficiency and the sufficiency are there. And this unbiasedness we have discussed in our last video, and from this last video we have seen that there may exist more than one estimator which is unbiased for the same sample. Like if I consider this example that we already discussed in our last video, if I consider a sample of size m 5 like x size, and I consider the two estimators t1 and t2, and then clearly sees that both the estimators are the unbiased estimator of mu. How you can prove that any of the estimator is unbiased? So you have to prove that this is the unbiased estimator of this. So means you have to prove that E of t1 is mu, E of t2 is also mu. So once you will prove them, you may analyze that there exists more than one estimator for the same population is there. So therefore there is a need to measure the another parameter for the good estimator, that is called as the consistent estimator. So as I told you, the consistent estimator is nothing about the spread, that is the variance as illustrated in this figure. So once we are talking about this point estimator, one have the smaller variance represented in this blue color, while this green color is represent for the larger variance. Our target is to find the consistent estimator which has the smaller variance. So what is the definition of the consistent estimator? Is any estimator Tn, which is a combination of this based on the sample size, is said to be the consistent estimator if when Tn converges to this parameter, this in probability. So you have to prove its convergence in probability. So we already discussed about that. What is the definition of the convergence in probability? That is whenever when we discuss about the weak law of the last number. So else you can write this definition in form of this: T of n minus of gamma is less than epsilon is converges to the 1, or else you can write in terms of the here it is a greater than of the 1 minus for all of the n. So this is the definition related to the weak law of the large number or the Chebyshev inequality. Now, since it is clearly sees that the consistent estimator is totally dependent upon the n approaches infinity, it means what we can say that the consistent estimator is concerning the behavior only for the large sample of the n, but it is nothing about the behavior for the finite value of the n. Finite means for the small n. Therefore, we can say that if there exists any consistent estimator Tn of this, it means this is convergence to here, then there may exist infinitely many such estimators. For example, if I say T of n is the consistent estimator of this, we can define some new estimator like Tn dash by using this. Then we can clearly see that whenever n approaches infinity, this part becomes a 0 and this will goes to here. And since this is the consistent estimator, so therefore Tn dash is also be the consistent estimator irrespective of the value of the a and b. So you can take a as 2, you can take a as a 3, you can take a as a 4 and so on. So this is also be the consistent estimator. So hence if T of n is the consistent estimator, so because this n is an infinite value are there. Now how you check that whether any estimator is said to be the consistent or not? So in order to check whether this condition, we will discuss about the sufficient condition. What are those sufficient conditions? So if we are able to prove that for any of the estimator, if we prove that expected value is a finite value and the variance is a 0, then that estimator is a consistent estimator of whatever this expected value converges to as n approaches infinity. So whenever there is a statement like you have to prove that this is a consistent, you have to satisfy these two properties. Like say one example, show that in a sampling of the normal distribution, the sample mean is nothing but the x bar is a consistent estimate. So we can try to prove this with the help of the two methods. We can use one is a sufficient method or second is the by definition. So let's discuss the first one with the help of the by definition. So what is the meaning of that? In order to prove this sample mean is a consistent, that is you have to prove this part, and by the definition you have to prove this result. So whenever there is a inequalities there, we have to always start with the Chebyshev inequality. So what is the Chebyshev inequality suggests to you that this will be here. What is the K is? Nothing. K is nothing but my K sigma. Here is K sigma is nothing but epsilon. And what is the sigma is? Sigma is the variance of this x bar. That is sigma square is nothing but variance of the x bar. So now our task is to find firstly the variance of the x bar. We all know that if xi is follows the normal distribution with mean mu and sigma square, then x bar is follow again the normal distribution with mean mu and variance is sigma square by n. So therefore, what is the value of this? This is nothing but sigma square by n. So what is the value of the sigma? Sigma is nothing but sigma by root n. So if you substitute the value of here 1 by k square, so what is the value of the k square is epsilon square divided by sigma is nothing but here, that is square root of variance of x bar. So if you substitute the value of here, this is a k square, so it will be square. So once you substitute the value of sigma square by n here, you will get this value. So what will happen as n approaches infinity? This will goes to the 1. So this will satisfied. Hence, x bar is the consistent estimator. So this is a simple proof. Otherwise, you can prove the second method with the help of the sufficient estimator. What is given to you that a sampling of from the normal distribution. So I can consider x size sample of size n from the normal distribution. So it means each of the x size has a mean mu, variance is sigma square. Now in order to prove that sample mean, that is the x bar is here. So to prove that x bar is a consistent estimator, what we can do prove that sufficient condition is we can try to prove that E of x bar is mu because I need this mu, and variance will goes to 0 as n approaches infinity. So I can start with the first part, E of the x bar. So x bar is this. I can take the E of this on the both side. So what is the 1 by E of the ax is 1 by n is outside. What is the E of the xi? We know that E of the xi is the constant value. So if you substitute the value, you will get mu as n approaches infinity. On the other hand, if you calculate the variance of this, you can calculate 1 by n. What is the variance of the x1? This is a sigma square. So this is a sigma square. This is a sigma square. So what is that? This will be n times sigma square. So if n will be cancelled out, so it will be sigma square by n. And what is the value of this as n approaches infinity? 0. So therefore, E of x bar is a finite value and variance of x bar is approaches 0. So therefore, x bar is the consistent estimator of this mu. Look at the another example is that if T1 and T2 are the consistent estimator of gamma 1 and gamma 2, then you have also proved that the linear combination of this T1 and T2 is also be the consistent estimator of their linear combination where A and B are constants. So what is given to you that this is a consistent estimator. So what is the definition of this is for the T1? E of T1 is goes to this gamma 1 and variance will goes to 0. E of T2 goes to this gamma 2 and variance will be 0. Now in order to prove that this is the consistent estimator of this, so what you want to prove that? You want to prove expected value of this is nothing but my here and the variance of this goes to 0 as n approaches infinity. So I can start with the left hand side firstly. You can see that I can open this bracket. What is the value of this? It goes to the gamma 1, it goes to the gamma 2 as n approaches infinity. The first part will satisfied. Similarly, you can find the variance. What is the variance of the ax is a square of this. What is the variance of the T1 is goes to the 0. This is goes to 0. This is there. So since these two properties are satisfied, hence this is the consistent estimator of this. This is the required proof. Look at one more example is there. If xi is a random sample observation of the Bernoulli variance x, which takes the values, it means xi which takes the value 1 having the probability p and takes the value 0 when the probability is 1 minus p. Show that this is the consistent estimator of this. So that's quite easy. Can you find the mean of the xi's? So you can easily find the mean of the xi's. What is the mean of the xi's? Xi into pi. So what will happen? This is 1 into p plus 0 into 1 minus p. This is nothing but my p. Also you can calculate the variance of the xi's. How you can calculate the variance of xi's? E of xi square minus E of whole square. So what is the E of xi square? This is 1 square into p plus 0 square into 1 minus p. what is the E of this is P square. So that is P minus P square. So this is the E, that is the mean of the xi's are my P and 1 minus P square. Otherwise, you can also see that this is the Bernoulli distribution, and you know that the mean and the variance of the Bernoulli distribution are here. In order to find the consistent estimator of this, I can firstly consider this as sum of the xi's. I call as a H is my sum of xi's. And you know that if xi's follows the Bernoulli distribution, then what will the sum? This sum will follows the binomial distribution. And what is the mean of the x? What is the mean of the H? So can you find the mean of this? This is x1 up to xn. So what is the mean of this? This is nothing but np. Similarly, you can find the variance of this is np into this. Or you can see that H nothing is followed by binomial distribution. Now, in order to show this is the consistent estimator, in order to simplify this, you can see these are the same thing. So I can consider G is there. So therefore, this expression, so our target is to prove G of 1 minus G the consistent estimator of this. How you can prove that? That's very simple. So in order to show this, I can firstly prove that G is the consistent estimator of P. So I can firstly try to prove G is the consistent estimator of P. So for this, what you can to prove that? In order to prove this, I can prove G of P is converges P as n approaches infinity, and variance of G is approaches 0 as n approaches infinity by the sufficient condition. So we can start with this. What is the G is my here. What is the E of xi is nothing but the H. So I have the mean of the H, variance of the H. I can start with this. My target is here. So I can simplify this simply. What is the G is here. This quantity is nothing but my H. 1 by n is outside, E of H. What is the E of H is expected value of the mean of the binomial distribution is np. So this is cancelled here. So this property is satisfied. Now in order to find the variance of G, you can see this is 1 by n square. What is the variance of n? What is the variance of the H? I have derived this. So 1 n will be cancelled out. So it will be here and it goes to 0 as n approaches infinity. So what is conclude from then? This is satisfied. So therefore, G is a consistent estimator of P. But my task is to prove 1 minus G into 1 minus this is the consistent estimator of this. So that's quite easy. Now you can use this property. So if I consider a function x of 1 minus x, because my function is G of 1 minus G, which is look like here. So you can check whether this function is a continuous or not. Yes, this is a continuous. So once you can prove that this is a continuous function, then you can use the invariant property. What is the invariant property of the consistent estimator? If T of n is the consistent estimator of this and f is a continuous, then f of this is also the consistent estimator of G. So since we proved that G is the consistent estimator of P and f is a continuous function, so it means f of G is also be the consistent estimator of f of P. So if you substitute what is the f of G, this is nothing but the G 1 minus G is the consistent estimate. What is the f of P? P and 1 minus P. So that's the quite simple proof. You can substitute G is here. So that's a simple proof of these results are there. So what is the invariant property that we will discuss in our next class? That is what is the invariant property of the consistent estimator. Till then, you can simply follow this link for finding the more updated videos on the point estimators, and the statistics are there. Till then, best of luck students. Happy learning.